Okay, let's start. So, only one piece of chalk today. So, yesterday we discussed the concepts of chronological and causal future and past. And today we'll take them forward and you'll begin to see also what use they are. So today this is lecture 10, I think. So today we'll take these ideas forward, but before I do that, let me just emphasize that what we are trying to derive or define and derive are statements and theorems about general spacetimes. And why we are trying to do that in such a careful and precise way is because we want a criterion for a good spacetime that we should allow in physics. There is absolutely no guarantee that you can do physics sensibly on a weird spacetime. This issue doesn't really arise in many other theories of physics, because the space or spacetime on which the theory is defined is fixed, and then it's fixed to be the Euclidean space for spatial theories or Minkowski spacetime. But if you allow an arbitrary spacetime, you could probably, or you can easily allow one which doesn't admit any sensible physics to be done. Physics requires an initial value problem, some differential equation, you give the initial conditions, you evolve it. As you know, in Minkowski spacetime, the initial conditions are at some time t equals 0. But here we can change the definition of time as we feel like by a coordinate transformation. So what initial conditions make sense? So these are the kind of questions we are trying to deal with. But I do want to emphasize that whatever theorems and definitions we've had so far, even if I may illustrate them sometimes with very simple spacetime like Minkowski or Minkowski with one point deleted, these results are supposed to be valid for generic spacetimes. So the discussions are for general spacetimes. And
so
here,
weird spacetime means spacetime having singularities, or there is
there are many other things, not just singularities. Good, thank you for asking. No, not necessarily singularity. It could be a very nice smooth spacetime, but it could be quite unsuitable to do physics. We'll see that. Now, one problem I face, or anyone faces in teaching this subject, is that we try to draw diagrams to illustrate what we are saying, but the diagrams are drawn actually in a Euclidean two-plane, which is the board. Even if you stretch your imagination and you imagine it is Minkowski, it's still a two-plane, or at best it may be three-dimensional, but it's completely flat. I can't really draw diagrams for you that are diagrams on a curved spacetime. Therefore, some of the things we are trying to rule out don't even make sense in Minkowski spacetime. Like, there are some strange behaviors which are possible. We may try to write some theorem that this behavior is possible or not possible. But typically those strange behaviors anyway won't be possible in Minkowski, so I can't anyway draw them. So you have to take all drawings with a pinch of salt. That's all I'm trying to say. You have to understand what the drawing is. Not like a drawing of in any other subject of physics, where you're actually trying to represent a situation in flat space or flat spacetime. So please be very careful and ask me if there's any confusion, as many of you did yesterday actually, or some of you. But yeah, good. So now we want to, continuing with yesterday, we will define the following thing. So imagine I have a point P and another point Q, always in space-time. Maybe I drew this badly. Let's put the point Q here. Then the way I have drawn it, the forward light cone of P will contain Q, and the converse is also true. The backward light cone of Q will contain P. So if you like, this whole thing I'm working with I plus, not J plus, so the chronological future. So this is all I plus of P, this shaded region, while this other shaded region is I minus of Q. Now let's consider this rectangle. What is it? It's the intersection I plus of P intersection I minus of Q. And we give this a name. It's called the causal diamond of P and Q. So we write it as DPQ. We put the earlier point below, the later point above. At least that's my convention. And we call this the causal diamond. So causal diamond is always with reference to a pair of points P and Q. So it's the intersection of the causal. Oh, sorry, I said wrong. Completely wrong. These are all J. Causal, not chronological. I was using the right word, but I wrote the wrong thing. So it's the causal diamond, not the chronological diamond. So causal always means time like or null. And for that I need to use the J spaces of yesterday. Those are the causal, future and past. The chronological are I plus and minus. So actually the causal diamond is just J plus P intersection J minus Q. Now this diagram looked very nice and I got this doubly shaded region as the causal diamond in this example. But it's very easy to have another example where the causal diamond is empty. I simply choose P here and Q here. Now the J minus of Q is this, including that, and J plus of P is like that. And you see that the causal diamond is empty. So it can happen. So there's no guarantee given any pair of points that the causal diamond has anything in it. But if there is, then it has that rectangular shape. Okay, now what's the use of this? So let's imagine there is a causal path starting at P and ending at Q. I claim that that path necessarily lies inside this. Okay, why? If the path tries to go, so let me write it here. Causal path P to Q must lie inside this causal diamond. So it's the space inside which all the causal paths lie. So first let's argue that. So let me start here. I can go out from here. To be causal, I should go in any direction which could be null or time-like. Okay. Now I can be here and wiggle around and I will reach Q. That's a causal path. Supposing I try to do something more brave and I go outside here. Now, once I'm out, I'm at a space-like separation to Q, so there's no hope to come back. That's not a causal path. If I want to try and go out here, I already am out in a space-like direction, so this is already not allowed. So basically, if I'm not allowed to go in a space-like direction, I must fit inside this box. That doesn't mean though that any path inside the box is causal. You can easily find paths which are not causal but still inside the box. How does that work? Well, I might go out from here in a very nice time-like direction and then I may decide to become space-like from time to time. That's not a causal path, but it's still a path from P to Q inside the box. So it's only a one-way implication. If it's causal, it's in the box. If it's in the box, it may or may not be causal. Okay, is that point clear? Yes.
What if you have some points removed in this region?
Yeah. So if the points are not there, then they are not there in J plus of P or in J minus of Q, and that's that.
So that
they'll be missing.
rectangle will not be.
Yeah, of course. So indeed, I mean, it could have all kinds of things in it. So it's yeah, exactly. So thank you. So in general, it might not have a simple rectangular looking structure even. What is meant by this rectangle is boundary of the light cone. But again, the light cone is defined at P only for an infinitesimal distance. Then if I go here, for example, to continue the light cone, I must find the new light cone at this point, this point, this point, and in that way build up this line. So it's not a straight line in a general space-time. That's I think what you're saying, first of all. Similarly that. And then once I do that, from here I start constructing light cone boundaries going up to there. And then inside this, whatever happens, whatever the space-time is doing, it's doing. If there are points missing, they are missing. Okay. So obviously, if it's missing, if there are points or regions missing, I can't have paths that go into those regions. But surely I can have paths out of those regions. Mind you, it really helps that we are not discussing geodesics here, because if we were worried about geodesics, which we will be in a few minutes, then life is quite different. Okay, a missing region might make it impossible to find a geodesic at all, for example, but it won't make it impossible to find a time-like path, because if it does, if there is no time-like path from P to Q inside this, that also doesn't disagree with anything I'm saying. All I'm saying is that if there is one, if there's a causal path, it must lie inside DPQ, and converse is not true. So if there's no causal path, there's no causal path. In any case, here we gave one example where anyway there is no causal path from P to Q, and it may happen also even if Q is, it may happen in principle if space-time is doing something weird there. Okay, good. Now, now we come to geodesics. So we bring in geodesics briefly. So can we go from P to Q? I imagine these are like the points up there, which have a non-trivial causal diamond by a time-like or null geodesic. And I'll remind you that while a general path can be partly time-like and partly null, a geodesic can't do that. We've already discussed that earlier. Geodesic, if it's time-like, it's time-like everywhere. If it's null, it's null everywhere. So this is a problem. The answer is no in general. And this is because in a given space-time there simply may not be a way to go from P to Q via a null geodesic. But there's a nice theorem which basically says that if P and Q are not too far apart in a certain sense, which I'll define, then there is a unique time-like or null geodesic going from P to Q. So definition, it's called a convex normal neighbourhood. Of a point P. So there's U, let's call the neighbourhood U of a point P is an open set such that for all. So we can find a convex, I will see that, but a convex normal neighbourhood is associated to one point. But now it's going to say that for all pairs of points Q and R, they don't even have to be P. Could be one of them could be P or need not be. There will be a unique geodesic for all there is such that all Q are connected by a unique geodesic. And the theorem is that, so we'll call this thing CNN for short, convex normal neighbourhood, always exists. Let's illustrate this with a drawing, which might help. Supposing my manifold is something very strange, then from Q here to R here, there may not be an obvious, for example, there might suppose, well, I could turn this upwards, but there might not be a time-like or null or space-like. There might not be a geodesic, or there could be more than one geodesic. For example, if this disk is missing from the space-time, and Q is here and R is here, then the best geodesic you can get might, the shortest paths you can get might be like this, but they may not satisfy the geodesic equation. Okay, because they actually don't, in some sense, minimize the distance. They only minimize it because that hole is missing. And there may be more than one that does that, but also they may not be geodesic. So a lot of things are possible, but the CNN theorem says that, okay, don't take the whole, this is the whole manifold. There is some part of the manifold which is free from this problem. It can be as small as you like, but an open set. Okay, in this part associated to a point P, I can pick any 2 points Q and R, and there's a unique geodesic joining them, but it may be space-like, time-like, or null. That depends on the separation of Q and R. And you can also refine this a little further by saying that in particular, this is a trivial implication. I haven't yet proved this theorem. I'll just tell you, say some words about that. In particular, let me draw the diagram again. And this is my convex normal neighbourhood U. Then from P itself, supposing I take one of these Q and R to be actually coincident with P, what are the points that can be accessed by time-like or null geodesics from P? For that, I should just draw J plus of P in the whole manifold, and then consider the part inside my convex normal neighbourhood. Okay, now the theorem I wrote guarantees that there is a unique geodesic from P to any point here, but since this point is now inside J plus of P also, therefore that unique geodesic has to be either null or time-like. It can't be space-like. That's a causality. Okay, so the first part of the theorem just is about the existence of an open set U, and the second part is about getting time-like, or so here you have a, so I'll take the point Q here and P here, then we have a unique time-like or null. Now, although I am not going to spend much time proving this theorem, and I'll refer you to a proof in a book or 2 books, it's very important. The uniqueness part is very important.
Sorry, I could not understand the definition of convex normal neighbourhood.
What's the question?
So, how are these points Q and R related to P?
No, they are arbitrary points inside that neighbourhood. I wrote
It
it
can be any point.
such that all Q and R in the neighborhood are connected by all pairs of points are
All Q
connected
and R
in that neighborhood, in that set U. So
And
I start with P, I find a neighborhood which encloses P, and now the theorem says that any 2 points in that neighborhood, but not necessarily outside that neighborhood, are connected by unique geodesic. It depends where P is in the manifold. If you think U is a neighborhood, that means it surrounds P. So if I move, imagine a manifold which is awful, it means I can go into any corner, wherever P happens to be. I can go close to P and find a very small region surrounding it, which is free of the madness which is going on in that manifold.
What is this uniqueness statement?
The uniqueness statement is that there is a uniqueness statement is that there is a unique geodesic between P and Q. So I said, see, in Minkowski space-time, there is a unique geodesic between any 2 points. It's the straight line, right? Now that uniqueness need not be there in a generic manifold. So I showed you an example where I had removed a hole, but you can also have an example, maybe more useful, where let's say I have some matter, but it's only gravitational matter, maybe it's dark matter, okay? And now I'm looking for geodesics from here to here. So it might be that there's a geodesic like that. This is what is called gravitational lensing, and another geodesic like that. I'm not saying that this is not a hole necessarily, but the hole, this matter over here is distorting space-time in such a way, hypothetically, that the geodesic, the shortest the geodesic path, the path solving that geodesic equation, has more than one solution. Okay, and it is gravitational lensing because we see from Earth that light is coming from 2 different directions, but it's actually light of the same object. It's the same image but being replicated in different directions. So here the geodesic is non-unique. Okay, but why is it non-unique? Because of something which is distorting the manifold in some place. Okay, if that distortion was not there and if the manifold was flat, then the geodesic would be quite straight. And here I'm not caring whether it's space-like or time-like or null. In Minkowski, it would be straight anyway, always. Okay, so in Minkowski, it's always unique. That's my point. So here it's non-unique in general, but now supposing instead of putting my point here, I just put it there, far away from this thing which is messing up the geometry, then it will be unique. That's the context of the theorem. Yes.
And what about this time-like or just null?
Oh, so far I didn't say anything about what type, but now I added a new thing, which is that I intersected this convex normal neighborhood with J plus of P. It's a new space. It's a subset of U, and also a subset of J plus. It's the intersection J plus of P with U. So now if I start, if this is J plus of P, then this point is P, then any point Q in the intersection of J plus P and U can only be connected by a null or time-like geodesic, can't be connected by a space-like geodesic. So with that, I have narrowed down the possibility of the unique geodesic to be either null or time-like. Yeah, 1 second, he had a question, yeah.
So I was just confused. You said earlier that if there is a hole, and you said there are to be paths, but they minimize the distance, but they're not geodesics.
Yeah.
How is that happening?
Yeah.
Geodesics should be the ones which.
I don't think that's. If you cut out a hole, that I think may not be true. Because you see the geodesic. Let's imagine I just have a flat. Let's say I have a flat space-time, and this thing is missing from it. Minkowski now. So this is x and this is t. Geodesic equations is solved by a straight line.
Right.
Okay. Remember also what is a geodesic? It's not a path which not defined as a path which minimizes or maximizes anything. If it was, we could never have a null geodesic because it just gives me 0. So it doesn't really. There's nothing I can change there. But here, with this, without removing this hole, the geodesic would have been that, and that's the unique solution of the geodesic equation. because that equation in Minkowski is x mu double dot equals 0. There is no Christoffel symbol term. So that's a straight line.
So like in
But
this
now-
example, can we say that there are no geodesics between
Yes.
those 2 points?
Yes.
But there are paths, and then we can minimize the.
We can minimize the paths, but that's not a geodesic. So if we are trying to look for things which solve the geodesic equation, we simply won't find them, and it's because of this hole here. But if this is a point Q and this is a point R, it just means that we were trying to find geodesics between pairs of points where some non-trivial topology is occurring in between them, I mean intuitively. But the theorem says that I could always pick an open set here such that any points Q and R in that set have no such problem. And basically it's topological in nature, because it's saying, look, tell me whatever problem you have over here that is preventing a geodesic to exist from Q to R. Once you tell me, I'll find a neighbourhood of R which is sufficiently small but still open, so that any 2 points in that at least have a unique geodesic connecting.
And this would be a consequence of the manifold being housed off?
Yeah, that's part of it. So I'll just come to the proof in a minute, but I'm not going to go through it in detail. But let me I'll say some words. Yeah, there's a question.
I was just thinking of a somewhat maybe pathological situation. Let's consider 1 plus 1 dimensional Minkowski with a spatial open interval removed.
Okay.
Then the point at the end of the interval
Yeah.
does not admit any Cn, right?
Yeah, 1 plus 1. So this is x, this is t. You want to remove just this interval, or you want to remove for all time or only for this time?
Just
Okay, fine. You can do that.
Yes. Now the point at the end of this interval lies in the space time, but it
Okay.
does not admit any Cn. It looks like.
Good point. Okay, let's see. Thank you. So the end point of this doesn't lie in the interval because the interval is open, so it lies in the space time. And there should be a neighbourhood of P. I think it's okay, because in the manifold with this removed, so if this was not removed, and let's say this is P, good example. So this is the set U I would have liked to take, right? But I can't take it because this line is removed. So I just remove that part of U. Now you may think U is not an open set, and it's not an open set in the topology of the original Minkowski space-time, but it is an open set in the topology of this space-time with that line removed. I believe that's correct. You can check up on it, but I think that is the case. So because the openness of the open set is not just what it looks like and whether it contains some point or line missing, but whether it's open in the topology of the submanifold. This is now a submanifold, or it's not even a manifold. Well, maybe you can make it a manifold with boundary, but for a manifold with boundary, topology is actually, you can check up the definition of manifold with boundary. So in that, I'm glad you brought this up. Supposing this is a manifold that down here extends to infinity, but up here it actually has a sharp boundary. Okay, now inside you may say that the open sets look like this, roughly like disks. But what are the open sets for points on the boundary? It turns out that these are the correct open sets, and that still gives me a topology. And in that topology, I am guessing that U will be open. Yeah. Good. Now, as for the proof, so one thing about the proof is only the last part involving J plus of P brought in causality in any way. Otherwise, it's just a statement about manifolds and geodesics. And it turns out it's a theorem in Riemannian geometry. So it can be found in standard texts of Riemannian geometry. One such text, let me at least give you the name, is Hicks' Notes on Differential Geometry. It's a good and I think reasonably compact textbook that you may want to refer to. Volume 1. Okay. So as far as the the first part is so the fact that there exists a convex normal neighborhood, that you can look up this. And the second part, it is discussed in Hawking and Ellis's book, but I think it's reasonably obvious, because once all you have to do is take that theorem and intersect it with J plus of P. And you know what is J plus of P. And you know that inside J plus of P, by definition of it, every curve, every geodesic time-like or null must lie in J plus of P. So it must be, so this unique geodesic must be time-like or null in that. It can't possibly be space-like, and there's no other kind of geodesic. Okay, good. Any more questions? Please feel free. These are very important and somewhat difficult things to grasp. So, yeah, as I said, the uniqueness of the geodesic between 2 points in a suitable convex normal neighborhood will be used in proofs of singularity theorems. So, better to be clear about it now. Okay, so now we are going to, this is little bit completes the discussion of yesterday. Had it been possible, I would have gone until this point and like to stop. The next topic or subtopic is globally hyperbolic spacetimes, and this needs quite a degree of preparation. So we'll first give a bunch of theorems which allow us to define this concept, which is extremely important. Now, one little point of nervousness is that if I lose this chalk, we are done for today, because there's absolutely no other chalk here.
Should I bring from something else too?
Well, you could either do that, or you could wait first for there to be a crisis and then bring it. Let's see how long I can hang on to this. But I'm really afraid it won't be long. And there's a huge stock of chalk sitting down in mine at Scribe Plus down there. Okay. Yeah, okay, good. Thank you. Maybe it's better, yeah. Okay. Okay, at least I'll write a few things, then I can repeat them for him when he's back. Definition. So, we want a concept of a subspace of our manifold such that no time-like signals can go from one point on that space to another point on that space, and such a subspace is called achronal. Chronological we always use for time-like. Thank you so much. So, I'll keep one. I think I'll keep an emergency one inside the drawer. Okay. So, a subset. Now here I have not said that it's a submanifold. It could be anything. It could be a point also. It's just some set of points or space in M is called achronal. Again, this is of absolutely fundamental importance. If there is no time-like curve, in M connecting a pair of points. Yeah, so I guess S can't be a single point, otherwise this doesn't mean anything. At least it better have 2 points. Okay, so now let's think what this means, and there's a little surprise because it's not as simple as it looks. So let's consider an example. Take our favorite example, literally the only example we can ever draw, which is 1 plus 1d Minkowski. So now if I have a set like this is achronal, because there's obviously no, if I have a point here P and a point here Q, then I can join these points by the straight line or by this curve or by that curve or even by that curve, but none of those curves is time-like. They'll always have a space-like path because after all the points are space-like separated. So in that sense, this interval is an achronal set. I could also tilt it. I could have taken my achronal set to be like that. So P and Q are still space-like separated, and again it's achronal. This is also achronal. This is also achronal. Right?
So every point outside the right cone can form.
Yeah. So that is exactly the statement that they are space-like separated. So space-like separated looks good, but actually it's not sufficient. I'll give you now a counter example. So obviously, of course, if P and Q are time-like or null separated, or actually not null but time-like separated, then obviously there's a time-like path between them. That's the whole thing. They are in I plus, one is in I plus of the other, then obviously that is not achronal. Okay? But now there's a very nice example which we can actually do in Minkowski space, but we need two space dimensions, x and y. T is still vertical. And we are going to draw a subspace of this, which is a helix. So it will go like this. Okay, so this is my subset S of the space-time. Now you have to understand that this is actually, each of these is approximately a circle slightly tilted in the xy plane, and then it's being copied upwards. Now you can ask for the slope of this, and it looks like the slope is doing that, but that's only an artifact of my diagram. I can make a helix that is everywhere space-like. I can also make one that's not. So basically, if I actually look at the angle at which t is, the rate at which t is increasing relative to my movement in space, if that becomes too large, then obviously I'm going time-like. So I can take a helix and I can stretch it so that it will be everywhere time-like, or I can compact it till it's everywhere space-like. So what I'm trying to draw is everywhere space-like. So it is space-like, but is it achronal?
You can connect them.
So what I can't do here, I can't connect this point to this point by a time-like curve, but I can connect this point to this point by a very simple time-like curve. If this is P and this is Q, they are different points in the space-time, but they are the same point in space at different times. And so actually if I sit at P, I'm in M, the Minkowski space-time. I sit at P and I say, oh nice, right now I'm on this space-time curve S. Few seconds later I notice I'm not on the curve anymore. Few minutes later I find I'm back on the curve. It's not a closed curve, it just happens that it's winding in this way. Okay, so it's a time-like, so therefore I can send a time-like signal from the curve to the curve, so it's not achronal. And the existence of such paths proves that, not achronal. So we can say that achronal implies it should be everywhere space-like or null. Because if it's anywhere time-like over any region, however small, then I'll have a time-like curve between those two pair of points. But the reverse is not true. Just being everywhere space-like or null doesn't make it achronal. Okay. There's another nice way to define achronal which is equivalent. Another definition. Another way. F S is achronal. Okay, we already gave a def, so we can call this a theorem or a lemma. S is achronal if and only if I plus, now it's I plus. Earlier in causal diamond it was J plus, now it's I plus because we're looking for time-like things to be absent. So I plus of P intersection I minus of Q is empty for all P and Q. This is all the paths you can reach from P by a time-like curve. By definition, this is all the paths ways in which all the paths that reach Q by a time-like curve. So if you want a time-like curve from P to Q, it has to be in the intersection of these two things. Actually a lot like the causal diamond, but it's more a chronological version of it that is restricted to time-like. Okay. So if this is empty, then the space is, for all pairs of points, then the space is achronal. It's pretty obvious. It's equivalent to the other definition, just a way of writing it. Okay. Good. And now comes a please again feel free to ask questions, and or even if you think it's going too fast, I'm happy to repeat anything you want. Because we are going to hit a couple of theorems that are really crucial, and one of them is going to come up right now. Okay, crucial theorem. For any set M, for any set S, you remember that I have defined I plus of S as the union of I plus of all points in it, and I also defined the boundary of I plus of S. So now the theorem says that this is I'm putting this in brackets, codimension 1, achronal set. Why did I say codimension 1? That's a trivial part of the theorem, because I plus of any point is already of the same dimension as the manifold. We stressed that yesterday. Because it is all points in the manifold that can be accessed by light signals from S, and they can go out in all possible directions. They can't go faster than light, but they can certainly go, so signals, not light signals, any signal, can't go faster than light, but it will certainly span a volume of space-time of the same dimension as the space-time, because it can go in all directions. So I plus is of codimension 0, but then del of I plus is its boundary. Boundary is always one dimension less than the bulk, and so this is already codimension 1. So that's just mentioned in passing that it's codimension 1, but this is the theorem. And there's a second part to the theorem, which is slightly more difficult to imagine. Moreover, S is embedded as a topological submanifold. Of it. M is the full manifold. So we are saying that this codimension 1 set, right now it was only a set, but we would like to know if it's a manifold. Turns out you can't prove that it's a differentiable submanifold of M, but you can prove that it's topological. And we discussed yesterday the difference. It means that continuity is preserved, but not necessarily differentiability. if you want a very vague sense of what that means, a differentiable path would be one which is smooth. So here's an example of a differentiable path. Here is a path which is not differentiable, but it's still continuous. And here's a path which is neither differentiable nor continuous. Okay? So this bend loses because there is no unique derivative of the path coming this way or coming that way. Okay? So this path, you could say, is a topological submanifold of two-dimensional Euclidean space. Okay? This one would be a differentiable submanifold. Now, if this was not just like this, but it had some breaks and all, then maybe you had to say something weaker. In this case, okay, you can say it's just a disconnected manifold, but if it's higher dimensional, it could be much worse than that. Okay. So now let's look at the proof, two parts of the proof. So,
Can you please explain what do you mean by topological submanifold?
I just thought I just did, and also I did it yesterday, didn't I? I wrote three kinds of things. I said topological structure, differentiable structure, and Riemannian structure on a manifold. The first, topological is the most basic. You cover, but I'll explain it again. You cover the manifold with open sets. You demand that the open sets be homeomorphic to regions of Euclidean space. That's how you cover the manifold with open sets, and you get coordinates. Now you have transition functions between overlapping patches. That's the key in the definition. But those transition functions, you simply assume they are continuous but not necessarily everywhere differentiable. Then it's a topological manifold. If you make them differentiable, then it's a differentiable manifold. Okay, so the first part, let's do the first part. First part is easier to state. Del I plus the boundary of I plus of S is achronal. Very short theorem, very short statement. So let's call this 1 and moreover is 2. Okay, so proof of 1. So we are going to assume the contrary, and we'll get a contradiction. So contrary means del I plus of S is not achronal. So then there are 2 points. P and Q, both in this space and connected by a time-like curve. Okay, so in particular, such that Q lies in I plus of P. Okay. So if the space is not achronal, then there must be at least one pair of points which are connected by a time-like curve. So by choosing P, labeling P and Q, interchanging them if necessary, one of them is in the chronological future of the other. Okay? But now we very quickly get a contradiction, because yesterday we proved that I plus of P is a subset of I plus of S. Okay, when P is in boundary of I plus of S, I plus of P is in I plus of S and doesn't intersect with the boundary. So now Q being in I plus of P is in I plus of S. So Q is now in I plus of S, and also by the starting assumption in the boundary of that. So Q is both in I plus of S and in its boundary. Remember, this is the chronological future, so our intuition is that this is inside the light cone and this is on the boundary of the light cone. Can you be both? But our intuition is not good enough. Instead, we simply notice, we already saw the result earlier, that this is an open set. So we are saying Q lies in an open set but also on its boundary. This can't be true. Open set and its own boundary are disjoint. Okay? But I plus cannot intersect with del I plus. So that's a contradiction. And therefore we conclude that indeed del I plus is achronal. Notice that we really didn't say much about S itself. S could have been a point. All our theorem reflects the properties of this thing, which is always codimension 1. Whether S is a point or a line or a blob makes no difference to the dimensionality. It makes a difference to what is this space, but not any difference to its dimensionality. Because it's the boundary. So I plus is obtained by taking a union over all I pluses of points in S. But then whatever that union space is, we go to its boundary, and that is what this space is. And it is that space which is achronal. Now, for the manifold property, this proof is a little difficult to grasp. But let's draw a picture. So here is del I plus, well actually the picture should look like this. S is some set, and here is this boundary thing is del I plus of S, and this is my point P. Okay. Now, again we use the theorem. So this theorem yesterday is being used twice. I plus of P is contained in I plus of S. The chronological future of this point is contained here and does not touch the boundary. That is what we proved yesterday. Okay. Now if that is so, what can we say about I minus of P, the chronological past of P? It must be in M minus, so this is the backslash is used by mathematicians to denote deleting some subspace. So it should be M minus this thing because it's the complement of this, but that's not all. It should be open. All I pluses and minuses should be open, and that will happen only if I minus the closure of I plus. Okay. If I don't do that, I plus has a boundary which it doesn't contain, then it will be, if I just subtract I plus from M, then the boundary of that will be contained. So this space won't be open. So this is a correct statement. Now let's draw them here. Again, one is struggling to draw things properly, but roughly this is I plus of P. This is I minus of P. And now let's consider a small neighborhood of P and try to set up a coordinate system. And if we can set up a coordinate system, then it's not difficult to argue that this whole space I plus of S, del I plus of S, is embedded as a topological manifold. So, yeah.
The contradiction was that I plus of S and boundary of I plus of S have to
are disjoint because I plus is open.
No, but then in that the pathological example, the R11 minus interval
still open.
No, there I can imagine an open set whose boundary contains one of those endpoints of the interval.
Yeah, but then that's not. Yeah.
Not in the manifold.
Yeah.
The minus.
Yeah, they are in his manifold. I think you have, okay, good. So I think you have to revise this theorem for manifolds with boundary. What happens is a manifold with boundary is technically not a, I should have said this earlier, manifold with boundary is not a manifold as per the definition of manifold. The reason is a manifold is something where you can map every region of, you can cover it with charts, each of which is homeomorphic to a open disk in Euclidean space. A manifold with boundary says that it's a collection of points such that either the neighborhood of every point maps to an open disk or to a half open disk with boundary, because I drew a picture for you showing you that if this is the boundary, then these are coordinate charts, but the ones which are here are these, including that line, and they are still open in the topology. But you have to then work in that topology, and probably you need to refine this theorem if you are working with a manifold with boundary. Good question. All the questions that people ask are good questions, but really, so it's very helpful. Good. So now back to this point. So now I can certainly go an infinitesimal time-like distance like that. Okay. So I try to draw a curve or a vector field like this, and I'll just call it del by del x0. That means it's a time-like vector field, and I define this direction, which I can choose arbitrarily as long as it's in I plus of p, and just call it the time direction. Now the interesting thing, this picture is a little busy, so I'll delete some of it. Now we are going to focus around this point. Now the interesting thing is, this vector field, I produce it and I come here, okay? And obviously by continuity I'll come out on the other side. Now can this curve hit back on del I plus of s? If this is where it's intersecting del I plus of s, can it then again intersect I plus of s? It's a time-like curve. Answer is no, by the theorem we just proved, which is that del I plus of s is achronal. So this curve intersects del I plus of s exactly once. So at every place where it does intersect I plus of s, I can give the coordinate of that place to be the value of the affine parameter of this time-like curve is the time value, and then I can set up an arbitrary spatial coordinate system xi, where I goes from 1 to d minus 1. And now I can repeat this for other points p on x in a continuous way. And now I can't give you a rigorous statement, rigorous proof, but it's intuitively clear that if I do this thing of drawing a time-like curve intersecting del I plus of s only exactly once, and I keep transporting that along del I plus of s, I will eventually cover all of del I plus of s with this coordinate system. Okay, or at least I'll cover this open neighborhood, then I can repeat for another neighborhood. Okay, the main point is that I'll be covering it in a continuous way. I don't know anything about it being differentiable, but I know that it will be continuous. And this was a bit brief, but my notes have slightly more details. But also you should look up, if you want more details of this proof. Oh God, where did I write that? Oh, did I forget to write it? So this is theorem, both of these parts 1 and 2 are theorem 8.1.3 of Wall. I doubt you'll find anything different from what I said, because whatever I've said is really what he said, but at least you'll find it in print. If you find a better way of saying, of giving this proof of the second, see, first part we proved, it was very easy. First part was simple non-intersection of I plus of S with its own boundary. That was easy. Second part is just the statement that it is embedded as a topological manifold. This will be useful in singularity theorems, but I've only given you an idea. This is a very common method of proof, by the way, to take an open neighborhood of some region, set up a coordinate system, and then argue that it can be transported along the whole space. Okay, any questions? Okay. So, moving on from that, so we are building up many little building blocks which we'll assemble in a little while, hopefully today, to define the concept of a Cauchy surface and globally hyperbolic spacetimes. One ingredient was this achronality of del I plus of S. Another ingredient is the behavior of curves. So now curves are paths. So consider an arbitrary path x mu of lambda. As I said, we are not necessarily considering geodesics, though we can apply these considerations to geodesics if we want. So generic path. So let me make the following observation, that supposing I have a future directed path. So this is x mu of lambda, and lambda is increasing this way. So lambda is just a label for the points. So it's a parameter labeling points on the path. Now there are actually 4 different things this path can do going into the future. What are these 4 things? Extend it to the future. Of course, you can also extend it to the past. It will be similar. So 4 possibilities. Maybe there are more, but I think this encapsulates the basic ones, and probably the others can be stated in these terms. So 1 goes to infinity. Now this, if the manifold is non-compact and it has some infinite region, then this curve can go on forever. That's one option. Second option obviously is that the curve stops somewhere. But there are actually 3 ways in which it can stop. One is it just terminates at P. And that's an option. The third one, you still have this point P, but the curve tends to P as lambda goes to infinity. Okay, so actually for any value of lambda, it doesn't actually reach P, but if, so to say, it slows down. So as lambda gets larger and larger, it gets arbitrarily closer and closer to P. So you could say P is a limit point of this curve. Now these two are not actually that different, because you can reparameterize lambda such that lambda going to infinity, which is here, which is there, at lambda going to infinity we reach P. You can use some function like tan inverse or something, and it will terminate at finite lambda. Okay, so they are not that different. So 2 and 3 are really the same. 4 is like 3, except that I removed the point P. It's not in the manifold. But again, the curve tends to P as lambda goes to infinity. This is certainly allowed. If I delete a point from a manifold, it's only a point that's been deleted. Any neighborhood of it is not deleted. And therefore, I can define a curve as a function of lambda such that for lambda larger and larger, it just gets closer and closer to P. It never reaches P, and that's just as well because P isn't also there.
Where is the point P on the manifold?
Anywhere, but it's a deleted point. Where meaning?
As in, you're saying extending to future, right?
Yeah, no, so these are, whenever I say a point P, it's not at infinity, because infinity is not a place, infinity is a limit. So there it goes to infinity of the manifold. That means I assume the manifold has a region that is infinite in its parameterization, okay, and then the curve extends all the way there. So obviously it just goes as far as it can. It just keeps going forever in our intuitive thinking. In these it terminates, but it terminates in a different way. In these two cases, it terminates at or arbitrarily close to a point P of the manifold, which is in a finite region of the manifold. And in this last one, the manifold has a point missing. So I'm not saying this is always the case, because some manifold may not have a point missing, but let's suppose the manifold has a point missing and the curve we are talking about terminates at that missing point. You can imagine more fancy ways for a curve to terminate, but these are some basic ones. Now the interesting thing is, now the property we want to define is what is called inextendable. So a curve should be inextendable if I can't extend it. So which of these four will you call inextendable? Huh? Sorry?
Second one?
No, actually.
First?
Yeah, first one is clearly inextendable, it's future inextendable. I'm not worrying about the past. If the same property is true in the past, then it's also past extendable, but we can worry about one at a time. Okay. So this, did I say causal curve? Okay. Of course, curves may not extend to the future, so you should have stopped me here. I should have said causal path. Otherwise, this whole discussion doesn't make sense. So the path is everywhere, either time like or null. It can change between them. So this one is future inextendable. Okay. This one and this one are future extendable. Because wherever this point P is, at that point, I can define a new curve which goes up to infinity and add it to the old curve, and now it's a curve of the first kind. So I can make it inextendable by adding something. Okay, so therefore it is extendable, and by extending it, I get to that case. And that's true in both of these cases. If it terminates at P, I can join the next curve to be one, I can take the next curve to be one that comes arbitrarily close to P above it and goes to infinity. If it tends to P, then I can take the future part to be a part which starts exactly at P and goes to infinity. Both times. Yes.
In the third case, you have to do it with the new parameter, because lambda.
Yeah, that's okay. We can change the parameter. Good, thank you. But we can change the parameter as we like. Now the fourth case is funny. It's also inextendable. The curve has run out over here, but I can't extend it by any means. Okay, because that point isn't there. So there's no way to join this to another curve such that I get a continuous causal curve going all the way to infinity.
But in the third case, it will also not be continuous.
It will be continuous. No, it will be continuous. In both second and third case, I will make a continuous curve as follows. This is what I just said from minute ago. If it is this case where it includes P, then I add another curve which doesn't include P but tends to P. If this one tends to P, then I add another curve which includes P. So it's continuous. It passes through P, and of course it can pass through P because P is there. If P wasn't there, it couldn't do that. Yes.
So in the third case, if I plus of P were empty, then we could not extend it.
I plus of P were empty.
Or I guess we would call that first case.
No, we can't call it first case because P is some region of, it's not a limiting region of the manifold, it's in the manifold itself. But I thought we said that I plus is always d-dimensional, so I don't know if it can be empty. But let's think, maybe there's a weird case like that. Okay, to make the last point a little clearer, because actually once you think about what it means, these three are all quite clear. This is the slightly puzzling one, but what we could do is the following. Imagine a curve which is of the first type, going to infinity, and even here going to another infinity. Okay, and now I craftily come in, pick a point P and delete it from the manifold. Before I did that, this curve was inextendable, both future and past. After I delete this point, it's still inextendable. It actually breaks into a pair of inextendable curves. Yeah, exactly. So if I delete, so originally inextendable, after deleting P, it's still inextendable, but it's now a pair of curves. Delete P, not from the curve, from the whole manifold, then it becomes, breaks into a pair of type 4. So both are inextendable. Remember that everything is causal in this thing. Of course, if the whole thing was causal, then each of these pairs that it breaks into will separately be causal. Okay. Now if I, after I've broken them up, supposing I put the point P back, then both become extendable, and they are extended by adding the other one. Each of them is extended by adding the other one till it becomes inextendable. Let me now, this has all been a little abstract, let me now try to give you some impression why we are worried about extendable. So this is very rough, and I should have maybe given you this concept earlier. Rough meaning, don't read too much into it. Inextendable is like nothing we can do to extend it more. So this will give me some intrinsic properties of a manifold. The presence of an inextendable or inextendable curve will be some intrinsic property of the manifold. It's not something to do with human intervention. I'm just using that word lightly. But extendable really means some fool decided to terminate the curve for no reason. Some fool terminated it. Just an arbitrary choice. There was a curve, case 2, it should have been allowed to reach infinity. Somebody just brought it to an end at P by hand. Okay, you can't say that such a curve will ever tell me some property of the manifold. This being extendable, I can't say that something is bad about the manifold in the future. Just because this curve isn't seeing it, because this curve was just stopped by hand. Okay, but when I look at inextendable curves, then I can really talk, they really probe everything of a manifold, and they don't stop just because somebody decided to stop them. They stop for valid geometrical reasons, either because they actually don't stop but keep going to infinity, or they run out of steam because they are approaching a point which is missing, and then they don't have a choice. Of course, they could avoid that point, but then it's a different curve. Such curves will be there. If there's a missing point, there will be curves which terminate close to that point. There will also be curves which miss it. Yes?
So fourth one tells that the manifold is topological?
No, nothing tells me anything about the manifold as yet. I'm anticipating something we'll do many lectures later. For none of these tells me, see, existence of one curve is not going to tell me what a manifold is doing. Okay, I'll need to think of families of curves. Now we did discuss families of curves, namely geodesic congruences, and we'll have to implement these ideas in that context, which we'll do much later. Okay, so I'm just anticipating that they will that these ideas will be implemented in the context of a congruence. But now, if a congruence somehow fails to survive at some region of the manifold, I shouldn't blame it on the manifold if my curves were extendable. Because if they are extendable, they just ran out somewhere because somebody decided to make them run out or stop, and they could have continued. So that extendable exactly means could have continued, could be extended. That's all. Okay, good. Actually, we are doing pretty well. So we have two more, one theorem and one definition, and then we'll stop for today, and we'll be able to do Cauchy surfaces next time. Any more questions?
Can it not have a causal path that comes back to itself?
So I guess, we could, a closed path. Yes, we could certainly have a closed path. So let's see, why did I not say that? A future directed, because I don't have closed, I'm assuming there are no closed time-like loops, and this is a causal curve. So if it's closed, then it will be, itself will be a closed time-like, a time-like or null curve, and that we are not allowing. So there's no option for it. So this is the point, that a curve going into the future or past has to keep going unless it is blocked by something missing from the manifold, some valid reason as it were, and this is just an toy example of such a valid reason. It could also be that the manifold develops a huge cut right over there, not just one point deleted, but infinitely many points might be deleted. It could be anything. It could be that here it reaches heaven and here it reaches hell. I mean, these are all things we don't know, we want to explore. But let me say literally that when I follow a past inextendable curve, I'm actually going back in time from the present universe. Since the universe is now expanding, I'm going to the phase of the universe where it was contracting, and this will run out when it hits a big bang, if and when it hits a big bang. Okay, this is the intuition behind all of this. I mean, we are nowhere near discussing those things. There are many things to be done before that. But actually we are not so far also, but we are not, at the moment we are not going to be discussing those things. But my point is that to find out whether there's a big bang, Hawking worried about what do inextendable curves going to the past actually do. He didn't have to worry what extendable curves do if they are going back in the past, because those might stop for no reason, and we assume that whenever there is such a curve, we extend it so that it doesn't stop anymore. And then we focus our attention on the inextendable ones. Now if something goes bad, then something might be wrong with the manifold. We are really looking for possibilities of the manifold to go bad in some way, and we have to define what are all the possible ways. I hope that was a little bit helpful. Okay. By the way, it's easy to construct an example like this in Minkowski spacetime. Find a parameterized curve that runs out at some point and delete that point from the spacetime, then you will have an inextendable curve. Okay, so theorem, let x mu lambda be a past. You can do every theorem with past or future as you like, but this is past inextendable. And let me assume it's causal. So I am not saying that it's time-like, it's only causal. Okay. Then there exists a again past inextendable, time-like curve. What am I trying to do here? I am trying to replace my causal curve by a time-like curve in a certain way. Everything else is the same. That lies in the chronological future of this curve. I'll draw it and then it will be easier to see what's going on. So I have first a past inextendable causal curve. So let's take the worst case. It's just a null curve. That's causal. And this is not a boundary, this is actually a single line. It's an actual curve which is going, and it's inextendable, so it's going to go either till a hole or till minus infinity. So this is x mu of lambda. And the theorem is saying that, now what's the causal future of x mu of lambda? It's the union of the future light cone I plus of every point along this. So it's basically this side of it, without going too far out. So if I take the earliest point, now I don't know how to distinguish light cone from my actual curve. Basically you can access all of this. All of this will be I plus of x mu, you agree? Just in the chronological future of x mu. Okay? So the theorem says that there's a another curve which is here, and this curve x tilde is time-like. Here I have drawn x mu to be null, but it could also have had some time-like parts. So it could be null and then bend like this and then go straight like that. That's allowed. But in its future is another curve x tilde, okay, which is also past inextendable and lies fully in the future of this. Now this is inextendable, so this goes all the way to minus infinity. So lying fully in the future is something like this. It could approach as closely as we like to this, but it must always remain time-like. This is what the theorem is telling us. This is theorem 8.1.4 of Wald. What it does is it allows us to replace a causal curve which is inextendable by a time-like curve which is also inextendable. Now what could go wrong is that, okay, so why this theorem is needed I can't tell you now, that we'll find out when we use it. But remember, this curve is supposed to lie in I plus of x mu. That means it can't touch this curve. Okay? And you could imagine that it can't be too far away because we want to be in some region very close to this curve to avoid any other topological issues that the manifold may have. Now, if we had not put the inextendable condition, then we might have a problem that this curve could come and touch this one because there would be a point here where this one is ending. Okay, and that would be the last place where we can have a future light cone. We can't have anything beyond that. Then this would have no choice but to come and hit it, but then it wouldn't lie in I plus of x mu. It would lie in the boundary of, it would at least intersect the boundary at one point. So the inextendability is important. And this is related to convex normal neighborhoods. I'll leave it at that. So the proof is related to existence of convex normal neighborhoods. And I think I just said it, but I'll repeat. The existence of such neighborhoods allows me to think of a curve which is reasonably close to this, but deviates from it in some way, enough of a way that this remains fully time-like while this could have null segments. I should be able to undo the null segments into time-like segments. That's all I'm really trying to do. Okay, and I don't, because I can start by constructing a convex null neighborhood like this one, and then have this curve inside that, and then use the uniqueness properties that any two points are joined by a unique geodesic, and then I can keep modifying that continuously as I go down, with this curve getting closer and closer to this one, but never actually touching it. That's roughly how the proof goes. Okay, and now we have the last statement, which is now that we have prepared all the background, the last statement is very simple. I realize this has probably been the toughest lecture of all so far, but this is the material that we need to work with when we do the hard stuff of GR. But still, if there are any questions, otherwise I'll define the last thing, which is domain of dependence, and then we'll stop for today. Okay. So definition. The future domain of dependence D plus of a set S, which is taken to be achronal. And actually, for this definition, you impose an additional requirement that it's everywhere locally space-like. It could, if you remember, an achronal set could have been space-like or null. But for this definition, it's space-like. Actually, I'm still a little puzzled because different authors say different things. So I'll confirm that next time. Is the set of all points set of all points in the manifold, Q in the manifold, such that every past inextendable causal path through Q passes through S. Let's draw it. That will make it much easier to access, to understand. So, let's say I have a set S. Let's take a point Q and ask the question, from Q I draw every possible past inextendable causal path. Does it have to pass through S? It's a somewhat different question from earlier. Earlier, when we talked about chronological future and past, we said that the future is some place which we can access by some curve. Here we are asking a much stronger question, that given any curve going from Q to the past and which is inextendable, does it have to pass through S or can it avoid it? Okay, if it can avoid S going to the past, then Q is not in the domain of dependence, in the future domain of dependence. Only if it has to pass through S. Now, we can immediately see some properties of S. Earlier our sets S were completely arbitrary, but now we'll see, suppose S is a point. what is the domain of dependence of a point? Here's the point. What is the set in its future in the manifold of points such that all past curves from there which are inextendable are obliged to pass through P?
I plus
No, not at all. Just say, remember the statement. Q is in the future domain of dependence of P if every past going curve from Q passes through P. Every. Is it true that every past going curve from Q has to pass through P?
no.
Every, yeah, it doesn't, right? It can just pass around P. This is a D minus one dimensional space here. It's going to the past, all right. So with time going negative, it's going downwards, but doesn't have to pass through P. It can actually pass this way, it can pass that way, it can pass out of the board. So the future domain of dependence of P is empty, completely empty. Again, I emphasize, every Q is in the domain of dependence if every past going curve from Q, of course inextendable, that's why we spent some time on that, necessarily goes through the set S. Then Q is in the domain of dependence of S. And as I emphasize, necessarily, not that there is one past going curve from Q which passes through P, that's this causal or chronological future, but now it is every. So empty. When B plus of P is empty.
But it has to be inextensible.
Well, otherwise it would just stop. So if I allow extendable curves, then I can never have any domain of dependence because every curve need not pass through anything. I can never force. Let's first see some examples of actual non-trivial domains of dependence, then we'll see the answer to your question. So D plus over point is empty. Now what if I replace my point with a line? One-dimensional space line. What is D plus of that? What is the set of points up here such that every past going inextendable causal curve must pass through this line?
Triangle. This triangle.
Why should any past going curve from Q have to pass through a line in the past?
Oh, Q is arbitrary.
No, Q is in the domain of dependence if it satisfies this definition. I'm looking for points Q. Is there any domain of dependence for a line? We just established that for a point there is none, because if I go to the future of that point, not all past going curves need to pass through that point. So you must focus on the words very carefully. The question is, here's a line, it's a one-dimensional line, it's a wire. Do all past going curves from any point in the future of that line need to pass through that line? Or can they avoid it?
They can avoid it.
If
M is more than 2 or more than 2 dimensional,
uh,
then they can.
if M is more than 2-dimensional, then M is D-dimensional. So, yeah. So what is the so good? So the domain of dependence of a line is also empty.
You can extend that to any
Except
n minus 1 dimension.
very good. So the only sets S with non-empty domain of dependence we've given them a name before. They are hypersurfaces, which is the same as codimension 1. So indeed, if I was in 1 plus 1D, then obviously a line is blocking all of, basically you want this thing to be blocking the access of past going rays from Q so that they can't go further to the past without banging into this. Okay, and you can block it only if this thing has all the dimensionality other than time. Right? In 2 plus 1D, this should be a plane, spatial plane, XY plane. Then from here you have to bang into that plane in order to go into the past. In 3 plus 1D, this should be an actual block, and it should be also, it should be infinite if it's or it should be large. Okay, it may not have to be infinite. It should be large because, okay, what it should do is to prevent all causal curves from passing through. So we don't care if a space-like curve like that can pass without hitting it. We only care about causal curves. So this is sort of the intuition. So to have a domain of dependence requires to be a hypersurface, and then it may still not have a, I mean, it may have or may not have some particular domain of dependence. That is to be done case by case. We'll look at examples next time. So obviously D minus S is similar. For this we search among points in the past, causal past, that is J minus of our set S, and we ask which future directed inextendable curves pass through it, and if all do, then that point is in the domain of dependence. Yes.
One like a nitpicky point, but
Yeah.
when we say Q in M,
Yeah.
Do we mean Q in M or Q in M minus S?
Good. Well, Q is in the causal future. I think if we are doing it for causal, did we say? Yeah, I don't think it's M minus S, because I think domain. Good. So domain of dependence of any S includes S itself.
Yeah, that's
So,
just why it won't
so
be empty, it will
good. Thank you. Actually, my notes don't say that. Is P. Is that space. Thank you. It is a nitpicky point, but if there were no nitpicky points, my lectures wouldn't be needed at all. Roughly, we are trying to do things which involve lots of nitpicking, so it's good to do that. So exactly what you say. So there is no non-trivial, it's trivial because it's only itself, but it's not empty. Okay, good. Then there are various things. I think I should stop. But there are a couple of minor corollaries, and then immediately we will define Cauchy hypersurfaces and globally hyperbolic spacetimes, and all that will be next week. Any questions? Okay, then I'll stop here.